Hello! Today we will be going over the relative velocity equation for 2 points on the same rigid body. Let's go ahead and start by looking at our diagram. We will be considering a body beta rotating in the fixed frame F. And for F, since we are dealing with planar motion, we will only be considering the x and y axes with the I and j unit vectors respectively. On our body beta, we will be considering 2 points, P and Q, which are fixed points on this body. That means that the vector going from P to Q, RPQ, will always have a constant magnitude in time, but as the body rotates, its direction will change. So let's say the body were rotating clockwise. This would mean that the point Q would go downwards, the point P would go upwards, and so the vector RPQ would go from this upwards right position to more of a downward right position as time goes on. Now, considering this relationship between P and Q, since the magnitude is constant, it will be useful for us to define the direction of RPQ throughout time as its own quantity. We will define this to be u. Now, the way that we can find the direction of u with respect to time is by defining theta of time. So theta of time is measured from the x-axis to the vector RPQ, and so as this vector changes direction, theta will also change. Using this, we can define the unit vector u hat to be cosine of theta in the I direction plus sine of theta in the j direction. So let's go ahead and start relating point P and point Q together. Using basic vector addition, we can see that the position vector from our origin O to point Q is equal to the position vector from our origin O to point P plus the position vector from point P to point Q. Although it can be useful to know the position of the points with respect to our origin, we're looking for their velocities. And in order to get velocity from position, we will take the time derivative of that equation. So we can see that r dot OQ, dot meaning a time rate of change, is equal to r dot OP plus r dot PQ. To simplify this, we know that the time rate of change of vector O to Q is simply the velocity of Q, and that the time rate of change of the position from O to P is just the velocity of P. But now this last term is a bit more complicated when we're taking its derivative. We know that it doesn't change magnitude with time, but its direction does change with time. So the way we're going to write this instead is extending that vector into its magnitude, RPQ, times its direction, which we already defined to be u hat. So let's go ahead and take this derivative. We know that RPQ is constant, so we can pull it out of the derivative, and now we'll just be taking it with respect to u hat, which we define to be cosine theta in the I hat direction and sine theta in the j hat direction. Taking this derivative, we can see it to be RPQ times negative sine theta I plus cosine theta j. Now this derivative isn't done, however. We took cosine and sine as a time derivative, but theta also changes with time, so we need to apply the chain rule. So all we have to do for that is then add a theta dot at the end. Now we can take this section and actually simplify it even further. So we see that RPQ can be multiplied by theta dot in the k hat direction, crossed with cosine theta in the I direction, plus sine theta in the j direction. This cross product is equivalent to the expression above. Here, we can recognize that cosine theta I plus sine theta j is the same thing as u hat, and u hat times the magnitude RPQ is our original vector for position going from P to Q. So our final simplification of this is going to be theta dot in the k hat direction, crossed with our position vector from P to Q. Let's go ahead and plug this back into our velocity equation. So we see that the velocity of point Q equals the velocity of point P plus theta dot in the k-hat direction crossed with our position vector from P to Q. This is our relative velocity equation for 2 points on the same rigid body. So we have our equation for the relative velocity, but what does it mean conceptually? It means that if we are looking for the velocity of an unknown point Q, we can find it by adding the velocity of a known point P to this cross product. And this cross product is the change in direction with respect to time of body beta, and this is also known as its angular velocity, crossed with the position vector from unknown point to our unknown point. Now let's analyze this section a little bit further. So our change in direction with respect to time is always going to be in the k-hat direction since we're operating in the x and y plane. If we use our right-hand rule on that vector, we'll see that the resultant is always going to be in the k-hat direction. But why are we crossing this angular velocity with a position vector? Well, this is because our dimensional analysis needs to make sense. These two linear velocities are a distance with respect to time, but angular velocity is radians or degrees with respect to time. So we need to add this extra distance term in order to have those units be the same. That's all we have for today's video. Go ahead and check out some of the next ones using the relative velocity equation in examples. And thank you for watching. Go ahead and like and subscribe.